Hello everyone, welcome to part 4 of the chapter 3 videos where we are going to talk about something new, measures of position this time. Instead of measures of center and measures of spread, we're going to discuss a way to quantify the relative position of data values amongst all the other data values. So we'll be able to determine whether a data value is an outlier, for example, or whether a data value is an unusual amount, either unusually high or unusually low. And we're especially going to be using this idea of a z-score. And this must be one of the most important ideas from the whole class. And the z-score is going to tell us the number of standard deviations that a data value is from the mean for that particular data value. And so we saw before with the empirical rule, we're always bringing up the same kind of a bell curve. And this bell curve has some conventional markings on here, and I'm going to label the center as 0 because here I'm not actually labeling by particular data values, I'm labeling by z-scores. And so we saw before how we could talk about the percentage of data that were expected to lie within 1 standard deviation of the mean or within 2 standard deviations of the mean. And these markings are representing how many standard deviations from the mean we are, and these are also the z-scores because that's what a z-score is. And so we'll see over and over again plotting data instead of based on the actual values, based on the z-score, because then it's going to be easier to compare one set of data with another, since we will be able to talk about the relative magnitude of data values. And we've got a couple of formulas for finding the z-score, but what's important is that it's just telling us how many standard deviations a data value is from the mean. And so x is going to be our data value. The population mean is mu, so if we take the difference here, it tells us how far away a data value is from the mean, and then when we divide by the standard deviation sigma, this z-score is going to tell us how many standard deviations that value is from the mean. And since we're performing this subtraction, of course some data values could end up being less than the mean, so whenever we find the difference in this numerator here, it's going to be a negative number. So z-scores are allowed to be negative whenever data values are less than the mean, and they would be positive whenever data values are more than the mean. And going back to this idea of the empirical rule, remember that within 2 standard deviations of the mean, that's 95% of the data. And so outside of 2 standard deviations, or in other words, if a data value is more than 2 standard deviations from the mean, then we're going to be in these tails over here. And since the bulk in the middle makes up 95%, these tails are the remaining 5%. And this is going to be a convention for us that by default, if something is 5% of the data, or if a data value has less than a 5% chance of occurring based on this empirical rule, then that's going to be considered unusual. 5% or less is unusual. And we will see an example here using z-scores, which we're going to determine whether a child is malnourished or not based on the z-score of their weight. And we're given here that a population of girls has a mean weight of 44.5 pounds. So the mean of the population is 44.5. And then the standard deviation for the population is 7.76. And we would like to determine for a girl weighing 34.5 pounds, what is the z-score? And I'm just going to go into the formula here. It should be the data value, 34.5, minus the mean, which is 44.5. And then we will divide this by 7.76. And we can perform that in the calculator. And that gives us a z-score of negative 1.29. Of course, we always round z-scores to 2 decimal places. That's mentioned here. And this z-score, it was supposed to be that the child would be considered malnourished if the z-score is less than negative 2. This z-score is greater than negative 2, so the child is not malnourished. The child is actually nourished. And then this weight is a bit lower. We're going to do the same calculation, but for a weight of 27.4. This z-score I meant to say was negative 1.29. Now we're going to do it for the other weight. So we're going to actually find the difference between 27.4 and 44.5. And dividing it by 7.76, we will end up with a z-score of negative 2.20. And since this z-score of negative 2.20 is less than negative 2, this child would be considered malnourished. And now in this next example, we're going to get into kind of the main purpose for using z-scores, which is to discuss the relative value of data. And here we're going to be able to compare men and women, since the individual populations of men and women have a different mean weight and different standard deviations. We're going to be able to find the z-scores for how much men weigh and how much women weigh, and then compare the z-score to determine which individual is relatively heavier, either the male or the female. And so we have here, I'm just going to make a little table to organize the parameters that are given for us. It says that the average male weight is 183.4 pounds, and the standard deviation is 40 pounds. And for females, the mean weight is 156.5 pounds, and the standard deviation is 51.2 pounds. And so the question is, who is relatively heavier? A female who weighs 185, so that's going to be the value for the female. I'll put a little subscript F to know that that's the female. The female weighs 185, and the male weighs 200. Who is relatively heavier? So we should find the z-scores for these. The z-score for this female, it's going to be the data value, which is 185, minus the mean, which is 156.5, and then divided by the standard deviation of 51.2. Whereas our calculation for the male, our data value is going to be 200, and the average is 183.4, and then we would divide by the standard deviation of 40. And so I'm going to go ahead and calculate these z-scores. And we get that the z-score for the female weight is 0.56, whereas the z-score for the male weight is 0.41. Oh, actually, I'm rounding it incorrectly. It should be 0.42. Of course, as 5 would round up. And we can see that since the female z-score is more than the male z-score, the female actually is relatively heavier. And then for this question, would it be unusual for this female to weigh 185 pounds? Now, going back to our standard for something being unusual, unusual means that the z-score is greater than or equal to 2. Actually, we should say probably that the magnitude of the z-score is greater than or equal to 2, because a z-score of negative 2.5 would also be unusual. It's anything outside of either less than negative 2 or more than 2. And so that would not be unusual for a woman to weigh 185 because the z-score is only 0.56. If it was something more than 2, then it would be unusual. And now here's a very similar example that I'm going to skip for sake of time and carry on with a couple of more vocabulary definitions, which are going to be more ways that we can measure the position. The first measure of position that we saw was the z-score. Now we will have this other measure of position, which is the percentile. And what the percentile does is it tells you which percentage of the data is less than a certain data value. And so the kth percentile, it tells which data value has k% of the data less than it. And we have actually seen a percentile before, which was this measure, the median, because the median has 50% of the data value less than it. That makes the median be the 50th percentile, and we also will discover here in a moment another name that we can call the median. But let's just fill in a couple of blanks while we're at it. We have the 35th percentile. This would be a value that's close to the lower third. The point of the 35th percentile, it's this data value over here. And the percentiles, we call them by a capital P with a little subscript of which percentile. The 35th percentile, it's the data value that has 35% of the data less than it, which would mean that 65% is greater. And so it's separating the bottom 35% from the upper 65%. Similarly, the 80th percentile, that's going to be a relatively large data value because the 80th percentile, let's say it's here, it's going to have 80% of the data less than it. And so 80% is less, 20% of the data values would be more. And so it separates the upper 20% from the lower 80%. And then the blank percentile is the cutoff point for the upper 10% of values. The upper 10% of values being cut off, that means it's going to be a large data value up here, which is the 90th percentile. It has 10% more, and we call it the 90th percentile because 90% of the data are less. So it should be the 90th percentile. And then we've seen how to say it without any kind of context, but what about if a child is in the 15th percentile in height? You should get the feeling that this child tends to be on the short side because that child is the same height or taller than only 15% of the children that are the same age. And these other examples, they carry on the same way. But just talking a little bit more about percentiles and what we would refer to them even more commonly, we don't care necessarily to refer to every individual percentile. We're actually interested in this idea of quartiles, which the quartiles break up the data rather into just individual percents, so having 100 of them, there are just 4 of them. And the first quartile, it's also the same thing as the 25th percentile because it's larger than exactly 25% of the data. And then the second quartile, here comes the other vocabulary word that we can use to describe the median. It's the second quartile because it separates the lower 50% of the data from the upper 50%. And that means that it's exactly in the middle, which when we think of it that way, we call it the median. And then the third quartile, it is going to separate the lower 3/4 from the upper quarter. And that's also called the 75th percentile. And whenever we're going to find the quartiles, it's similar to finding a median, but it's kind of like finding the median twice because you have to split up the data into the upper and lower halves, and then you find the median of the data that's in the lower half and you find the median of the data that's in the upper half. However, the way that we're going to end up doing it, because it's just so much easier, would be to put the data into the calculator, and whenever we use the 1-bar stats, it actually gives us the quartiles as one of the outputs. And so we'll see how to do it here. Whenever we've got these final grades from students, we're going to find the first quartile, the median, and the third quartile. So I need to come into my lists and put these data into the list. And here I have mine in list 1. Now very simply I'm going to exit out of there, and I'm going to come over here to stat and then calc 1-bar stats. I don't need a frequency list. I'm just trying to find the 1-bar stats for list 1. That's the only place where I have any sort of data. And if we scroll down, we'll see where it gives us the quartiles. And so it gives us quartile 1 is 77. The median, which is quartile 2, is 86. And then quartile 3 is 94. And now using these quartiles, we're able to come up with another measure of spread that is called the interquartile range. And it's just the difference between quartile 3 and quartile 1. And so something that's nice about the interquartile range is that it is actually a resistant measure of spread. We have not seen one of those before because we had the range and we had standard deviation and variance. All of those are not resistant. But the interquartile range is resistant, and we're going to actually use the interquartile range to determine what data values should be considered outliers. And we'll see here a formula to determine what's going to be basically the lower breaking point and the upper breaking point for a data value to be considered an outlier. And we use this thing called fences. Basically, we'll have a lower fence, which is 1.5 interquartile ranges less than the first quartile. Any number that's lower than the lower fence is going to be considered an outlier, and then we've got the same kind of a situation for the upper fence. We take the third quartile, and we add 1.5 times of the interquartile range, and that will be our standard, so that we can say that any data values that are greater than the upper fence are going to be considered an outlier. And now using this data from before, which were the class grades, we can find the interquartile range, and that's just the difference between the quartiles, the third quartile and the first quartile. And 94 minus 77 is 17. The interquartile range is 17. So now we can use that to determine our fences. And we will have a lower fence and an upper fence. The lower fence here, if you can see the formula, we find it by taking quartile 1, which is 77, and then we subtract 1.5 times of the interquartile range, which is 17. And for the upper fence, we have a similar calculation. We take the third quartile and we add 1.5 times of the interquartile range. Now these calculations, I'm going to do them here on the calculator. And we will have that the lower fence is 51.5 and the upper fence is 119.5. Now when we're looking back at our data, if there are any data values that are less than 51.5, it's going to be an outlier. And you'll notice that there's this 43, which is an outlier. And then on the outliers for the upper end of the scale, we're looking for any data values that are more than 119.5, and of course we don't have any. And so there's only the one outlier of 43. And we're going to use this idea of outliers and also this idea of the quartiles to come up with a new graph. And that's going to be the subject for 3.5. And that concludes this video. And I will begin on 3.5 in the next one. So thank you guys for watching.